In our previous video introducing salt damage to porous building materials, we stated that salts are often provided from external sources. In this video, we examine groundwater as such a source and its transport into porous materials through capillary suction. In previous videos, we described how capillary rise depends on the pore size and contact angle, among other parameters. We saw that the rate of rise increases with pore size, but that the maximum height of this rise is inversely proportional to the pore size. In most practical situations, we must additionally consider the role of evaporation during capillary rise. This leads to an accumulation of salts, but also affects the position of the waterfront, which ultimately determines where salts may cause damage. The rate of rise is maximum at the base and decreases as the height of rise increases. This is due first to the increased viscous resistance as the height of rise increases, and second, to gravity that reduces the rate of rise until the rate drops to zero when the weight of the water exerts downward pressure that equals the upward pressure from capillarity. This effect of gravity was ignored in our video on sorptivity. Let us now add evaporation at the surface of our object. The rate of evaporation, illustrated by the vertical line, is independent of height. The net resulting rate of rise decreases. So, at the critical height hs, the vertical flux caused by capillary suction has decreased to the point where it is equal to the flux of vapor evaporating from the surface. Above the critical height hs, the waterfront retreats from the surface of the material because the rate of evaporation is slower inside. Its lowest value is at the center of the object, as shown by this additional vertical discontinued line. The height reached by water is therefore higher in the center of the element than on its surface. For salt solutions, such as groundwater, we must consider that the evaporation of water causes the salt concentration to increase. When the height is low, the excess salts in solution can diffuse back towards the bulk solution, while fresh solution is drawn to the surface. As shown here, this leads to a wet layer at the base of a masonry element without precipitation of solid salts. Above this height, the rate of supply of fresh solution is too slow compared to evaporation, so the salt concentration rises and precipitation takes place on the surface of the element. This external growth is called efflorescence, which is not aesthetically appealing, but does not damage the element mechanically. Above the height at which efflorescence forms, the rate of rise of groundwater eventually becomes slower than evaporation, so the crystallization front retreats into the masonry element. Salts then form in the pores and can exert crystallization pressure. Such situations are generally referred to as subflorescence and sometimes as cryptofluorescence. They can be damaging depending on the local supersaturation, the amount of crystals exerting pressure, and the material's tensile strength. The heights at which the above phenomena are observed depend on the transport properties of the masonry and its exposure conditions, such as relative humidity, temperature, and wind, as well as the wetness of the soil. Importantly, masonry is not a homogeneous material, as it includes a combination of blocks or bricks with mortar in between, all of which may or may not be covered by a render. The relative dimensions and properties of these components play an important role, and should be considered when conservative interventions are carried out. For example, the difference in pore size between the mortar and masonry elements would determine the direction of fluid flow, while sorptivities would determine the rate at which groundwater or wind-driven rain would be absorbed by either of these materials. In this respect, mortars based on Portland cement and having a low water content may be harmful as they would develop high strength and low sorptivity, tending to trap water in stone or brick. Traditional mortars based on lime, pozzolanic mixes, or hydraulic lime may tend to perform better in this regard. However, their slower hardening, in particular for pure lime-based mortars, can make them particularly susceptible to freezing damage when winter is coming, because fresh mortar is susceptible to freezing as it remains wet and weak for a long time. When examining the capillary rise of salts, it is important to remember that we deal with highly soluble salts that are hygroscopic and may dissolve or precipitate in response to changes in relative humidity. Therefore, changes in relative humidity may displace the height boundary between efflorescence to subflorescence, just as changes in wind or temperature may do. This implies that zones where efflorescence is visible may become problematic at another point in time, or may, depending on circumstances, already have potentially damaging subflorescence forming. In view of this, and knowing that damage increases with salt loading, removing salts when they effloresce appears as a simple and useful action to take to limit the risk of damage. Another consequence of dealing with soluble salts, and in particular mixtures thereof, is that they undergo various degrees of separation over the height of the element. Less soluble salts precipitate lower than more soluble ones. As reported by Arnold and Zender, this can imply that zones showing damage may be found between two moist layers, whereby the upper moist zone would contain the more soluble salts. This separation must, however, be evaluated from case to case, as it will depend on the salt mixture, the substrate properties, and the exposure conditions. In conclusion, capillary rise of groundwater in materials such as stone, brick, concrete, and adobe leads to the precipitation of salts. Damage develops when this happens within the pores of these materials, and the local conditions of supersaturation and salt loading cause the crystallization pressure to exceed the local tensile strength. While efflorescence is not damaging, zones showing efflorescence may also lead to subflorescence because of changes in exposure conditions and must therefore not be considered as perpetually safe.